Here are some data points: the size of a house and the price it's sold for. Your job: predict the price of a house you have never seen. The oldest, simplest, and still one of the most useful answers in machine learning is draw a straight line through the data. But which line? Out of infinitely many lines you could draw, how do we find the best one? That question and its answer is what this video is about. Let's set it up. Every straight line can be written as y hat equals w times x plus b. The hat on the y just means our prediction, not the true value. This equation has exactly two knobs we can turn. The first is w, the weight, which controls the slope, how much the price rises for every extra square meter. The second is b, the bias, which slides the whole line up or down. Linear regression model means finding the single pair of numbers w and b that makes this line fit the data as well as possible. But as well as possible is vague. We need to turn it into math. Take any candle line. For each data point, there is a gap between the true value yi and what our line predicts y hat I. That vertical gap is called the residual. It's how wrong we are on that one example. A gold line makes these gaps small everywhere. So, a natural idea: add up all the gaps into one number that measures total wrongness. But there is a catch. Some residuals are positive and the point is above the line, and some are negative. If we just add them, they cancel out and a terrible line could score a perfect 0. Watch. Flatten out the line to the average price. It ignores the data completely and the residual sum to exactly 0. A terrible line, a perfect score. Now square the residuals instead and the same line lights up with a huge error. That's a classic fix. Squaring makes everything positive, and as a bonus, it punishes big mistakes much harder than small ones. Take each squared error, draw an actual square on the gap with the residuals at its side. The area after square is the squared error, so the total wrongness of a line is the total red area on the screen. And notice, double an error and its square holds 4 times area. Big mistakes dominate. So this picture is why the 200-year-old name for this method is least squares. The best line is the one that makes the total area of these squares as small as possible. Averaging the square residuals over all endpoints gives us the mean squared error, our loss function, j of w and p. And remember, y hat is nothing mysterious, it's just w times x plus b. Substitute it in and read the formula carefully. For each point, predict, subtract the truth, square it, and average. Here's the shift in perspective that unlocks everything. J is a function of w and b. The data is fixed, the knobs are the variables. To see what that means, freeze the b knob for a moment and turn on w. Every setting of w produces one loss value. Trace them all out and you get a curve. A smooth valley with a single lowest point, the best possible slope. Our current W sits part way up the wall, and improving the line just means sliding down this curve. But we have two knobs. Turn P as well and the curve stretches into a landscape. Every location on the ground is a choice of W and B. And the height at the location is a loss, because the loss is the sum of squares. This landscape is a smooth ball. One single lowest point, no fake values to get trapped in. One honest caveat. We froze B at its best value for that preview. Our actual line has B stuck way up at 18. So here's where we really stand. Higher up the wall, finding the best line now means one thing: walk to the bottom of the ball. How do you find the bottom of a valley when you are standing on its slope in the fall? You feel which way is downhill, and you take a step. In math, which way is uphill is exactly what the gradients tells us. The vector of a partial derivatives of j with respect to w and b. So we do the opposite. Repeatedly update w and b by subtracting the gradient, scaled by a small number eta, the learning rate. Eta controls the step size. Too small and the training crawls. Too large and you overshoot the bottom and bounce out of the valley entirely. This loop compute gradient, step downhill, repeat is gradient descent. And it's the engine underneath almost all of the modern deep learning, which means we need those two partial derivatives. Let's actually compute them. Start with the derivative of j with respect to w. J is an average of square terms and the derivative of a sum is the sum of derivative. So we can differentiate one squared residuals and average at the end. Each term is something squared. So the chain rule applies. The derivative of u squared is 2u times the derivative of the inside. And the inside yi minus wxi minus b has the derivative negative xi with respect to w. Multiply through n, we get negative 2 over n times the sum of xi times the residual. The derivative with respect to b is the same story, except the inner derivative is just negative 1, leaving negative 2 over n times the sum of residuals. Pause and look at what these mean. Each gradient is built from the residuals. The errors themselves tell the parameters how to change. If predictions are too low on average, the gradient on b is negative, so subtracting it pushes b up. The errors. Now watch the algorithm run. We initialize w and b at 0, a flat useless line. Every iteration predict with the current line, compute residuals, plug them into our two gradient formulas, and nudge w and b downhill. Early on, the errors are huge, so the gradients are huge and the line moves fast. As the fit improves, residuals shrink, gradient shrinks, and step gets smaller and smaller. The ball settling into the bottom of the ball. The loss curve on the right tells the story, a steep drop, then the plateau. When it flattens, we have converged. This is the best line.